Hi everyone, welcome to your lecture 4. We are going to be focusing on spatial analysis today. So spatial analysis, we kind of refer to this as the real meat of GIS because spatial analysis is essentially what GIS does its best work in. You can make maps in a variety of ways outside of using a GIS software. However, GIS allows you to do spatial analysis that is essentially something a lot of other map making technologies will not allow you to do. So we're going to go through a few examples, kind of looking at how we can utilize spatial analysis to start out this lecture. We're going to start by looking at some black skimmer locations from 1976 through 1998. What you should see on the screen, hopefully, if the GIF is working, and I'll go back and forward one more time so you can see, is a movement of dots or data points on this map that are representing black skimmers. Black skimmers are a type of bird. So our research goals for our spatial analysis in this example is to utilize a long-term data set and examine landscape relationships with these water birds. We want to know, are colony sites randomly located with respect to their landscape composition? And we need to understand what layers we need to answer these questions. So here are some of our target species that are in our data set. First, we have what we mentioned, that black skimmer. We have common terns, we have least terns, gull-bellied terns, and herring gulls. So the rationale for selecting these species is that each of these birds has a difference in its feeding strategy. There's differences in the stability of their colony sites. Some of them have higher turnovers of their colony sites, like the least terns. Some have lower turnover, like the gulls. There's also some mixed species colonies within these birds. So least terns don't tend to mix, whereas the common tern, the gull-bellied tern, and the black skimmer do tend to mix within their colonies. And finally, conservation interest. So all of the terns and skimmers, these populations have declined in the last about 20 to 30 years. So there's interest here in understanding their presence on this eastern shore community, but also just understanding how their colony speciation is represented within this data set, so that maybe later on we can look at common data sets, or, ooh, the word isn't right there. We can look at current data sets and compare it to this. So our methodology here, we're going to make a map of the locations of the colonies for each of these species. To do this, we will digitize our map and we'll use GPS coordinates. Then we're going to create random colony locations within our survey area. We'll do this by delineating our surveyed areas of the map, generating random pairs of coordinates that will fall within these areas, and then finally we'll have 642 randomly located colonies in our map. So our landscape data is collected from NOAA data, CCAP land cover data from 1988 specifically, and we have a variety of classes that we use, which are open, grass, shrub, forest, and marsh within this analysis. So you'll see here in this table, we have our classes, we have the source CCAP classes, as well as their habitat descriptions. You don't need to worry about that too much, but this is just essentially our metadata. Then you'll see that we have 200, 500, 1,000, and 5,000 meter distances for our colony locations. These are our buffers that we are using in our analysis. The results when we run this analysis is that averaging across all the times, there are strong differences between our landscapes associated with both our real and our random generations. You can see that the effective colony for black skimmer, common tern, least tern, and gull-bellied tern, the probability there is about 0.001, whereas our herring gull had a 0.351 probability. So essentially, for all but the gulls, we were able to distinguish bird colony sites from non-colony sites. So the spatial analysis techniques that we used, we combined a variety of layers, like our locations and our land cover data. We utilized data from one layer to then generate another layer, which are our buffers, right? 500, 1,000, 2,000 meters, and we generated random points. So our spatial data analysis usually requires more than one step and lots of intermediate files. And I'm going to do a quick pause on this recording if it will allow me to. Okay, hopefully we are recording again. My apologies, there's a bit of background noise, but we're going to continue on now with our spatial data analysis. So again, usually it takes more than one step and there are a lot of intermediate files. This visual example you have here shows you your input layer on the far left. We see that we perform our first spatial operation. Once we perform that operation, we have a new layer. We have our original input layer, but now we've created an additional new layer. We run another spatial operation that generates a second new layer, and then a third operation to give us our final layer output. So you can see here we have multiple intermediary layers to get from our initial input layer to our final output layer. Now, as we create all of these intermediate layers, it can be difficult to keep up with which layer is which, what layers had certain operations done upon them versus others. So you need to come up with some sort of a naming schema that works for you. You see here, this is an example of different ways to name layers. One is saying like my data underscore LL, and this is my data in geographic latitude, longitude projection. Another one is talking about your data using UTM, NAD3 specifically. One is talking about data with 12 different classes, another one with 4. Essentially, you need to come up with something that makes sense to you, the person who is creating these maps, to keep up with each layer of data as you go. Otherwise, you can get somewhere in the middle of your analysis, take a step away from your computer, come back, and find yourself taking too much time or more time than you would like to understand where it was that you left off and which layer you need to go ahead and run your next spatial analysis on. So now we're going to shift over into classification of tools. We've gone over a quick example of just essentially using spatial analysis to understand differences in colonies over time and different bird species. Now we're going to go ahead and actually look at some of the tools that we can use to do this type of spatial analysis. So we have a few toolboxes that we will very often use in this course, as well as you get into more advanced courses. These are your analysis tools, which are mostly vector tools, your data management tools, which are pretty general tools that you use in GIS, and then your spatial analyst toolbox, which is mostly your raster tools. Here's an example of something called input scope. So as we run spatial analysis, we have a different scope of inputs, as the name implies, to what is our input and our output, essentially. So what you get here is our very top example in this figure. This is a local input. So a local input is only using data from one location. You see on the left-hand side, we're just using that 1990 population density data. Our output on the right-hand side, then for that state, is a value of 20. When we use neighborhood scope, this also includes adjacent regions. So you can see instead of just one state, we have about 6 or 7 states now selected. So this operation, again, has adjacent states. Our output number is now 6, very different from the 20 that we had when we only used our local or singular state input. We also have a global input scope, which you can see here is utilizing everything within the vicinity of our original input. So the entire input data layer can have an influence on what our output is. We see here in this case that we're doing a global operation. We're doing a rank order by total population in 1990. So total population of this entire area. Our output is again 6. So part 1 of our spatial data analysis, we're going to talk about selection, spatial or non-spatial, classification, MAUPs or modifiable aerial unit problems, dissolving, and proximity and buffering. You'll see that throughout these slides, it's many slides, so I'll try to go through them somewhat quickly and just focus on what you need to know. You'll see, though, that on some of these topics, we'll focus a bit longer than others. So let's talk about picking our places first, our selections. First, we have something called set algebra. So this is utilizing less than, equal than, or greater than signs. When you are doing your algebra, or your Boolean algebra, sometimes we call it, you're going to see that which of these symbols you select is going to have a very direct and probably a very big difference, or yes, a difference on the output of what you get. So over here is a really good example. Starting on our upper left-hand side, we see that we have a value of state is equal to Vermont. Throughout all of the areas in this map, when we say state equals Vermont, we are only going to select the areas that are classified within the state of Vermont, as you see there. Now, if we say state greater than or less than New York, we're going to get everything else. You see, it's going to be less than or greater than New York. So New York itself is not going to be involved in what our output is, but everything that is basically not New York in this case will be selected in your output. We can also say, instead of doing a kind of a qualitative value of the name of a place, we can use numbers. We can say something based on its size or its area. So here we have area is greater than or equal to 1,000 square miles. Now, every single part of this map that has an area which is greater than 1,000 square miles will be selected for you to play with. And another example here, we can look at population density, and we can say that we want to select for population density where it is less than 250 persons per square mile. You'll see what is selected there from that Boolean algebra. So, and I may have misspoken a bit here. Boolean algebra is more and or not values, whereas our set algebra is a less than, equals, or greater. So let me clarify here and apologize. Set algebra is going to have a less than, equal than, or greater than value, whereas a Boolean algebra is going to be an and or not value. So these do a similar thing, but again with different terminology. If I want an area that has an area greater than 100,000, whatever our unit is, so area is greater than 100,000 and the farm income is less than 10 billion, I can use set algebra to kind of designate between my numbers here. And I can use Boolean algebra to say I need both of these qualities to be confirmed to have an output. We can also say that I want to select an area that is not equal to the state of Texas. So in my set algebra, I can say state is equal to Texas, right? I can also technically say state is less than, state is greater than Texas. But another way that I can go about this, which is a little bit more intuitive, is to just use Boolean algebra to say not, and use set algebra to say state equals Texas. And you'll see down here in our third example, we have a combination of our set and Boolean algebra where we have and as well as or values here. And we also have and as well as not values, all within the same equation, so that our output is something or some area where rainfall is greater than 1,000 and taxes are low. Or, if that isn't the case, the house cost is less than 65,000 and the crime is not high. You'll see this is something that's very useful in this example when you're trying to maybe find a piece of property, when you're trying to find a place to live. You can use set algebra and Boolean algebra in combination to I would say pretty efficiently figure out what areas qualify based on whatever metrics you're seeking. This is another visual example of Boolean algebra. For some people, it's a little bit difficult to understand Boolean algebra at first. I think that this is a very good figure to take a pause and look at if that's the case. You'll see that if we do A or B, starting at the top middle here, this is sphere A, this is sphere B. A or B includes everything of A as well as everything in B. You can be one or the other, and if you are one or the other, you're included. Now, if we ask for A and B, we're only going to have a selection of the areas that have both qualities, which means the intersection of this Venn diagram is the only place where the quality or the qualification meets both A and B because there's overlap. If you're not A or B, you're only going to be the sliver of C because remember now, when we have this Venn diagram, this portion of C is also A and this portion of C is also B. And then this middle point right here is both A, B, and C. So our output will not include any of these, anything that has to overlap with an A or a B. It'll only be C. Now, if we go to not A as well as not B, or not A and B, what we're going to get is that middle ground over there. We don't want anything that is both A and B. Now, you could see here, this is a little tricky and a little confusing. So I'm going to stop for a second. I'm just going to let you take a look at this. So you'll see again, everything that's selected here, there's portions of A that are selected as well as portions of B and portions of C. What we put into our criteria is that we don't want anything that is a combination of A and B. And the things that are a combination of A and B are in the center of this Venn diagram here. Essentially, this figure in the bottom middle is the complete opposite of this figure at the top right. And then finally, we have an example of what is A and B, or what is C. So again, we have this middle point, which is both A and B. We also have C as a whole. So hopefully this clears it up, and I'd recommend if one works better for you than the other, whether this slide makes more sense to you or this slide makes more sense to you, just go with what you know. So for spatial data analysis, selection can be based on both spatial and non-spatial attributes, and it can also be based on a selection of both. These selections can be an on-screen query, or they cannot be. So operations can be performed on these selected features as a group that's separated from the non-selected features. What this means is that you can have a map of the entire United States, you can select certain states in the United States, and run an operation based only on what states you have selected in this map. So here's an example of how to do an on-screen selection. You see here that there's a select button in your map pane on ArcGIS. Going into our geoprocessing, if instead we do select layer by attribute, you can go ahead and do these set algebras as well as these Boolean algebras. You can here see that we have where area is greater than, I think this is 100,000, and land cover is equal to, in this case, forest/shrub. So we see that we have our set algebra in these middle drop-down menus here. We have our Boolean algebra in these very first drop-down menus over here. We call this a logical statement. So here we're saying we want an area that's greater than 100,000 of whatever our unit is, and the land cover has to be a forest and shrub land cover. Once we hit run, that'll give us a selection of only these areas. And you'll see now we have in blue everything that we've been selecting in that query. Now in our attribute table, you'll see that you can click this box over here at the bottom left-hand corner. It's going to just be a set of blue rows, essentially. If you click that, you will only see rows or attributes, essentially, for whatever you have selected in your query. If you go back over here where you see this white line, white line, blue line, this will give you your entire attribute table where you have rows that have your selection included, as well as the things you did not select included. So pay close attention to that and use this to your advantage. You'll see, in this case, from what we just selected, all of our large forest tracts that are greater than 100,000 are now selected in our attribute table, as well as all of our land covers that also include forest and shrub. Now we have another tool here that we can do. We can right-click on land cover, and we can hit something called Calculate Field. So Calculate Field is only going to work on the selected forest shrub class in this case, because again, we have a selection going. It's not going to work on the entire map over here in the background. It'll only work on what we have a selection of. If you're ever confused if something is selected or not, what you can do is always look at this little portion of your map to see where it says selected features. If you have a value greater than 0, you have something selected. This is also something important to note as you're just generally working on GIS. If you are trying to run a tool and you're getting something wonky, it doesn't quite make sense why your output doesn't look the way it's supposed to, or maybe it's saying that a tool was run successfully, but you're not seeing anything. Look at your selected features and see if you have something selected. See if you have too many things selected, so on and so forth. Let me go ahead and remove that annotation and keep going here. So let me take it back 1 second and just show you that here in this calculate field, you can select the fields. So in this case, we use large forest. You can select the fields that you want to run some sort of metric or calculation on. You can, for example, create a field or create an output that says, I want to know where land cover equals large forest plus area equals 1,000. This is kind of similar to, let me bring us back, what we saw over here by selecting layer by attribute, but it's different because instead of selecting something on a layer, what we're doing is we're selecting something from a subset of data that we've already pulled out of that layer. If that is confusing to you, think of it differently in the sense of when we now have our subset here, which is our forest and shrubs in an area greater than 100,000, we can then, from this data, calculate metrics from this subset, essentially. So I'm not going to be able to get any sort of output for an area that might be wetland instead of a forest shrub, for example. I'm only going to be able to get information or a calculation from anything within the land cover class of forest and shrub. And this is without me at the moment having a new layer. I'm just running data on a sub-select or a sub-selection of my layer, but there's still no intermediate layer that I've generated yet. Instead of rambling on this point, I'm going to kind of keep going. And if this is something that you do have a question about, post it in Piazza and we'll answer that. So now moving on again to our select tool. We went through select by attributes, but now we're bringing it back over to select. This allows you to also do a manual selection on your screen. So some people like this, some people don't. It is something that you need to at least learned to be comfortable with, but many of us who are running GIS for a while, we're a bit more comfortable with it. We tend to go by select by attribute or select by location just because it's a bit more precise and quick. If you enjoy doing select manually with your mouse, you're more than welcome to do that. Just double check your work. So now talking about adjacency. So this is identifying our features based on a spatial criteria of being adjacent to a selection that we have. Here we're going to ask the question of which state boundaries contain major tributaries of the Mississippi River. So this form of adjacency is basically looking at containment. Which of the states contain these major tributaries? To answer this, we're going to select a layer by location. We can add or remove from the selection over here in selection type. We can also choose for one or many criteria. We can say whether it intersects, whether it's within a distance, whether it contains or completely contains. We can say whether it's within or completely within. So there's a lot of different criteria that we can use for the selection. Be very careful when you choose between things like contains, completely contains. The difference here is that I can say that Texas contains a tributary, but if Texas does not completely contain a tributary of interest, or does not completely contain that whole tributary, it could be excluded. If I want any state that even has a little sliver of a tributary, I would just want to select contains. If I only want states that completely contain that said tributary, I would select completely contains. So now on to classification and reclassification, grouping data. When we're doing reclassification, we aren't changing symbology, we're actually changing data. And this is something important to keep in mind. Your attribute table or your raster cell data will change as you reclassify information. But we're not changing the spatial data itself, we're just changing the attributes that are in that table. Essentially, we're going to go through an example here of small, medium, and large size grid cells here. Each one of these grid cells is again classified by its size, and that's denoted by the depth of color or the depth of the grayscale you see on the screen. These here are going to be our parcels that are reclassified by size. It seems like I might have, we're going to go through a few examples and then it'll bring us back to that figure. But essentially how we recalculate is going to the field calculator, selecting the field values. For raster, there's a reclassify tool that's very specific. So for a vector, we're going to do calculate field. Raster will do a reclassify. We can do it as well by selecting each class in our source layer and using a field calculator. If this is a very large data set, it's going to be very painful for you. And here's going to be an example of a reclassification before we get back to those grid cells, okay? So here on the top left, you see states within the USA, at least the lower 48, and you see that we want to select for states west of the main branch of Mississippi, as well as east of the main branch. We want the states that are west of the main branch to be assigned a value of 1. We want states that are east of that river to be assigned a 0. So what we did is we reclassified. Anything that is to the west of the river is going to be given, again, that 1 value. So Arizona, Arkansas, Colorado. Anything to the east is going to be given a 0 value, like Alabama, Connecticut, Virginia. The output is this map on the bottom right. You see everything to the west is now a 1. We don't have these state names anymore. We just have a value. Same thing happens here. So everything that's to the east of the river is now classified as a 0. Again, fundamentally, that state is still Texas, Oklahoma, Georgia, Florida, but it's now classified in your attribute table as either a 0 or a 1. This here is just something that I keep this in from John Porter's slides. It's called How to Lie with Maps. This is a really good read if you just want to kind of nerd out on something that's more map-based and understand how you can use tools like Reclassify, as well as other tools to essentially lie through your maps. If you reclassify information in certain ways, you can give your viewer a different understanding or a different thought on what reality is versus what it is. This is something that in, I believe, lecture 2, we go over a little bit of the idea of how you can lie with maps and aesthetics. This is an idea of how you can lie with maps using reclassification of data that is technically true, but the way that you visualize it or represent it can be misleading. Bringing us back now to our reclassifications and our classifications. Here we have our neighborhoods. We have 1,074 polygons. The population for our neighborhoods ranges from 0 to 5,133. We have 3 outliers above the value of 3,300. So essentially, we have a population ranging from 0 to 3,300 with 3 outliers that hit us at a maximum of 5,133. Our bar graph here shows us frequency of neighborhood population, or in a sense, there are 84 neighborhoods that have a population between 3,000 and 3,100. You see that little glip here? That is showing us a population between 3,000 and 3,100. There's a few ways that we can reclassify this data to get across a point of which neighborhoods have a higher population than others. Here's an example of an equal interval classification. So taking our bottommost value of 0 and our uppermost value of 5,133, if we split that number equally, divide it by 3 essentially, this is what your map outlook will look like. You're going to see that the areas that have 0 to about 1,700 residents are going to be this color white. The areas that have about 1,700 to 3,400 residents are going to be this medium gray. And our locations that have 3,400 to about 5,100 residents are going to be in this darker gray / black color. Now, that equal area classification is something that you just saw, but what if we do a natural breaks classification? If we do natural breaks, essentially we're saying within our data set, based on how many of these regions or how many of these clusters, neighborhoods per se, have X amount of people, we're going to put more weight in one group versus another. Instead of equally breaking it up, basically taking 5,100 divided by 3, we're going to take all of our numbers and see, oh, well, there seems to be a somewhat equal chunk of people living between 0 to about 1,100. But then we have a somewhat equal chunk of people living between 1,000 to 2,000, like that much of a population dynamic. So instead of having group 1 being 0 to 1,000, group 2 being about 1,000 to 1,200, we're saying group 1 is 0 to 1,000, group 2 is about 1,000 to 2,000, group 3 is about 2,000 to 3,000 with our few outliers. You see that this image looks very different. So on the left-hand side, that equal area classification, that's going to give us a lot of these cells or these neighborhoods that look like they have far more of a population or far higher of a population compared to our natural breaks. The English is not working today. Compared to our natural breaks classifications, where those areas of dark gray or black are now classified as a population of 2,100 to 5,100, and it seems like they're a bit more dispersed. I think the next slide will do a good idea or a good representation of the differences between the 3 of these. We discussed equal interval classification, equal area classification, and natural breaks classification. So your equal interval is the first one that we looked at. We see that basically most of these neighborhoods look like they have anywhere from 0 to 1,700 or 1,700 to 3,400 people within their neighborhood. Equal area, that's saying that, or let's say it's representing that it seems there are more neighborhoods that have about 1,200 to 5,100 people. This is based on the area of the polygons. And then our third one is the natural breaks classification based on both our interval and our area that essentially tries to give us the best understanding of, based on the range of our data set in numbers as well as the size of our parcels, what might be the best way to break this up. Now, I am saying that this seems like the best way to break it up, but focus on the title of the map slide here, How to Lie with Maps. Your classification has a very big effect on how your map appears or what your map aesthetic essentially is. So you have to be very intentional in which one of these reclassifications you choose. You can't just choose one and say, well, screw it, I'm going to choose one because this is the one I learned about last in our textbook or our workbook. You have to choose one based on the information that you have and the information that you are trying to process and get across. So now we talk about an MAUP or a modifiable unit. Right now, we've just talked about looking at effects of classification on a fixed spatial unit. No boundaries were changed. However, sometimes we don't have predefined boundaries, and we have to define boundaries for our analysis units. This is what a modifiable unit or a modifiable areal unit is. So we look at this example of cholera deaths. This is trying to show us the deaths associated with a contaminated well. That is represented by this kind of darker blue circle in the middle of our map. The wells are indicated by our triangles here, and all over this purplish color is showing us the range of these cholera deaths. So depending on the selection of your aerial units, the well may be identified as the problem, or it may be masked as the problem because you may have lumped it in with some other surrounding area. This here is an example, this is Tufts' example using Snow's cholera area of London. The left-hand side, the aggregation of individual deaths is done in 6 areas with the greatest number concentrated at the Broad Street pump, which you can see here in this dark gray/black color. In the middle, we use a different geographic subdivision, and the cholera numbers are nearly the same in 4 of the 5 areas. You see now it looks like all of these areas over here around the well have the same number of deaths. In the far right image, we see that in this aggregation of deaths, the 2 areas with the most deaths don't even include the pump that actually is the culprit. So how you define your areas, or how you essentially select your aerial units, has an impact on whether or not you see the well being the problem in the first place for these cholera deaths. So this is something I won't go into. You can pause on this and kind of read through it if you want, but this is essentially just talking about your aggregation units. These units use effect statistics determined in those aggregations, so this is kind of the math behind what you see here in a sense. But we're going to move forward and actually just talk about why MAUP is a problem. So the implication of MAUP is that definitions of boundaries alter statistical properties of those units. It's not necessarily good or bad, it just means that as you define boundaries, you are changing the statistical analysis that you output from it. So you have to be specific. It's called an MAUP, or a problem, because there's not a single good solution to address it. There is no one way to set a boundary versus another. So MAUP is something that we've all heard of and seen in our day-to-day life, and that is through something called gerrymandering. So this here you see is an example of a cracking style of gerrymandering where urban concentrations of Columbus, Ohio were split into thirds, and then each segment was attached to and outnumbered by largely conservative suburbs. We don't go too much into this in our summer course, but this is something that I would say, if you're very interested in it, look into MAUPs and gerrymandering, and essentially you can just type in geographic information systems or just GIS gerrymandering, and there are lots of very good videos that talk to you about how your local governments do this and how politicians themselves utilize these kinds of things and these kinds of maps to understand where gerrymandering occurs, where it's occurred historically, where they want it to occur in the future. I'll leave that to all of our Masters of Policy students and people interested in government, and we'll move forward to now talk about the dissolve tool. The dissolve tool is great because it allows us to eliminate boundaries between our polygons. It allows us to essentially simplify our polygon layers by eliminating the boundaries between an adjacent polygon that shares the same value of another one on a targeted field. So often we use it prior to applying an area-based selection, and it can be hard to select based on area if the contiguous areas are broken up into separate polygons. Dissolve allows us to bring it all into one polygon to therefore select on. So here's an example of a dissolve operation. You can see that before the dissolve, any area that was, basically any neighborhood that was shaded a white, a gray, or a black maintained its separation from the neighborhood adjacent to it, even if it shared that shading. Whether it was a low population, mid population, or high population density, each neighborhood was still separated. Once we ran a dissolve, we essentially said, if my adjacent neighborhood is the same population density as me, merge me together, merge me together, merge me together, to essentially get a much more simplified version of the map that you see on the right. So we're bringing back this example that we saw earlier when we reclassified these states with their names to being states that are classified as a 1 if they're to the west of the Mississippi, or states that are classified with a 0 if they're to the east of the Mississippi. So looking at this map, you can see, okay, it's pretty inherent that anything marked with a 1 is a certain value, anything marked with a 0 is another value. But isn't there a much easier way for us to visualize this by just saying, if it is to the west, merge it all together or dissolve all the boundaries of these states and label it as W, west. And if it's to the east, do the same thing, but for the east. To use the GIS dissolve tool, you'll just go to your geoprocessing toolbox and you will hit dissolve. From there, you can go ahead and select the polygon that you are going to dissolve. Its output will be the same name with an underscore dissolve. And then you can go ahead and say how you want the dissolve to happen, whether it's the area and perimeter that you want to dissolve. Um, this is something that will be very specific to what the task is that you're doing. Now we go into proximity functions. So proximity is essentially talking about closeness, or again, proximity of one cell to another. Sometimes we just want to know what is near a polygon. In this case, we're asking, is a planned house site within 100 feet of a stream? And how far is the nearest pizza restaurant or fire station to a place that I'm interested in? These proximity functions are really useful because essentially think of yourself as a home buyer. You want to know if the house that you're looking at might be close to a fire station. You want to know if it might be close to a highway system. You want to know if it might be close to a running body of water if you are somebody who's into outdoor sports and kayaking and such. Another reason that these proximity tools are useful is that your insurance companies use proximity tools to base the rate of your home insurance or your homeowner's insurance upon, or your renter's insurance in many of our cases. So, how close you are to a fire station, how far you are from a hospital, these all are factors into what your monthly payments are. So, bringing us back now to the slides. Our buffering and our proximity functions here, you can see for our points, our lines, and our polygons, when we run the buffer function for proximity, you can see that points just get this circle around them, lines get these kind of circular blobs around them, and polygons, those don't do buffers quite as well. Essentially, a buffer around a polygon will just be a larger polygon with a 5-meter buffer, 100-meter buffer, and what's not. The shape will be similar, but the area that it is consumed by for your interest in analysis will become larger. So again, you can see for our polygons, we have our input feature on the inside. You can see our buffer distance. And then this whole light gray blob here is now the output buffer. Anything that is within this gray blob will now be something that when you run an analysis, it'll run an analysis on this entire region. For a raster, it is essentially the same idea. Just remember that rasters, the value of a raster is the midpoint of its cell applied to the entirety of the cell. So instead of these kind of smoother lines, it's always going to be the entirety of the cell that is selected for your analysis. So here's another example of your buffers. The shading here represents distances to a water point, which is a form of a multi-ring buffer. I won't go too into this. Your workbook has you do a tutorial of using these multi-ring or multiple ring buffers that I think is phenomenal. You should absolutely read through that as you're going through your tutorials and make sure that you understand how to run that multi-ring analysis. I won't focus on this, but a raster buffer is an array of distances. You don't need to know this. You also don't need to know the mechanics of point and line buffering for our summer course. This here is just going to be a visual I'll go over really quickly with you guys of your buffering variants. And this is some point buffer examples. So this over here in the top left, or example A, is going to be your raw point layer. B is a simple one ring buffer. So it is an overlap of these points, and wherever that overlap occurs, we've told our system that we want to dissolve the boundaries. Example C is an example of a compound buffer, where instead of dissolving our boundaries for the overlap, we're just identifying how many times these cells do overlap. So essentially, we're kind of creating a Venn diagram in a sense. And then D is nested buffers. So the nested buffers here, you could see that on the outside of our buffer, it almost looks like our simple buffer with an overlap of dissolve. But we also have, similar to our compound buffer, these areas where we can see the most overlap. So we can see here that we have about 4 overlaps because of the number of rings it takes to get to our center point. We can also see that we overall have all of these points nestled within or nested within this certain buffer area. This is, again, not something that you need to take notes on and focus in this specific example. You just need to understand as you are running your buffers, there are different ways for you to visualize those buffers. There's the dissolve, there's a compound buffer to see overlap, you can nest your buffers, you can do multi-ring buffers. There's a variety of ways here. So here we're using a field in the attribute table to set the buffer distance for each of our individual lines. Here, for each of these rivers, the Mississippi River, the Missouri River, the Arkansas River, and so on, each of these rivers has a different buffer distance. Here we see some buffers around lines. We can see that sometimes when we run buffers around line features, like these rivers, for example, sometimes we get enclosed areas. It's important for you to know that anything within this enclosed area over here is not included in your analysis. So if you run some sort of a spatial analysis, the only things that are going to be included, let me go ahead and change colors here. The only things that are going to be included for your analysis are things within your buffer. So these bodies or streams here within your buffer, those are the things that are going to be included in your analysis. Anything in red or an enclosed buffer, which you also see another enclosed buffer right over here and right over here, for example, these will not be included in the spatial analysis that you run. So your buffer tool will look like this when you go into your geoprocessing toolbox and you select buffer. You'll see that you're going to have, again, your input feature. The output feature or output layer that you create is going to be called whatever the layer name is underscore buffer, or whatever you choose to change it to. You can then choose the metric that you want or the unit that you want and the value or amount of buffer for that selection. So in this case, you want a buffer that's 300 meters around your polygon. You select 300 for your distance and your unit is going to be meters. You can check, we typically don't play with these too much in Intro to GIS, but you have your side type and method. You can ignore those, but your dissolve type is going to be what you can play with, in that you find you'll play with a bit through your tutorials in this section. So in this case, we have no dissolve selected, but you can select dissolve all output features into a single feature, or you can dissolve features using the listed features unique values or combination of values. So again, bringing us back over here, there are multiple ways for you to kind of dissolve or create your buffers to show you different things. Here is a visual example of what that dissolve looks like. So your dissolve type based on your input, points, lines, or polygons. If you select dissolve type none, this is what your output will look like. You'll see kind of two separate buffers. If you select your dissolve type for all, then you'll see that everything, any sort of buffer that touches another buffer will morph with that buffer. Now to do a multi-ring buffer, this is going to be, again, in your geoprocessing toolbox, but it's going to be a separate tool. You're going to select multi-ring buffer. You'll see again that you can select multiple distances. So that's the difference here, is that instead of just one distance like we do have in our typical buffer tool, which you see right here of 300 meters, we actually have multiple rows or multiple categories of buffer sizes that we can choose. 10 meters, 20 meters, 50 meters, and so on. Now, your dissolve option is going to be different here too, that you can do, for example, non-overlapping rings, which is what's a really cool thing about multi-ring buffers. You can see our input for 10, 20, and 50. We get a buffer. Here's our 10 in the middle, our 20 in this blue color, and our 50 meters in this green color. So what our original yellow box was here on the left side, this original input polygon, is now represented as this multicolor and multi-ring polygon on the right. This is another visual example that we'll see here of multi-ring buffers. Again, our source point in the center, then we have our 10, 20, 30, and 40 meter buffers around it. So just another visual example. Now we move on to overlays. Overlays are merging attributes and physical features from different layers. So in this case, we're looking at one input to many inputs or many inputs to one input. What we want to do in an overlay is we want to take many inputs and have just one output. We're taking spatial data layer 1, spatial data layer 5. We run a certain function on them to get one output layer. So here's an example of that output layer, or that overlay, excuse me, that we're running, where we're taking layer A and overlaying it on layer B. So our overlay layer, or our output layer for an overlay, is going to have variables from A and B. You can see that it's almost like if you imagine a piece of Swiss cheese. Everybody uses this example. If you have a book and you put a piece of Swiss cheese on top of it, anywhere that those holes are, you'll be able to see through and see what the words are on that book. An overlay does a similar thing, but it says that any of the information on the bottom layer or on that book, I want to be able to see, as well as whatever I put on top of it. In this case, we have some water bodies in layer A that we're overlaying on a grid of, it looks like a road system or maybe a pipe system in layer B. Our output now has combined attributes for both layer A and layer B. So it's useful, but we can create multi-layer displays already, right? This table we can't get just by overlay, except for just by overlaying though. So again, you can get this by just creating multi-layer displays. In your contents pane, you can turn on 2 layers and you can play with the visibility of those layers to be able to see through them. But the attribute table is what is very specific and what is very necessary when we run an overlay operation. This is something that we can now run statistics or some sort of spatial operations on that gives us information from layer A and layer B in one solid place. So some of the operations that we use for overlays are spatial joins, intersects, unions, and identities. These can get a little bit confusing as some seem very similar to others. But as you kind of go on through your tutorials, you'll understand when one may be better than another. All of these will produce a new data layer that combines spatial and attribute data from the 2 layers that you are overlaying into one final output layer. There's also clip, and clip will preserve attribute table from one of the layers, but it will limit the extent of the data. We'll get into this. So here we have a vector overlay looking at a spatial join. A spatial join is something that you're going to be using very often in this course, I think from chapter 4 or chapter 5 all the way onwards. Here's an example of a layer that has our wells, as well as another layer that has counties. You can see that we have 5 wells within the wells layer. We have 3 counties within the counties layer. If we look at their attribute tables, this is what they look like. We have 5 IDs, and the owner of each of these wells, Dickinson, Murray, Smith, McBride, and Harris. For our counties, we have 3 counties, and they're called Black County, Cole County, and Fall County. When we run a spatial join, we're essentially saying wherever these spatially overlay or overlap with one another, we want the data to be merged for them into one final output layer. Then what we get here is, again, 5 IDs for each of the wells that we have, because we have more wells than we have counties. But for each of these wells that we have, we can now say what county it exists in. So we have 2 wells that exist in Cole County, 2 wells that exist in Fall County, 1 well that exists in Black County. This is really useful when you're trying to understand something like how many green spaces are there in Richmond, Virginia, right? You can have a map of all the green spaces in Virginia. You can have all the green spaces or the map of all the green spaces in Central Virginia. But if you very specifically want to know how many green spaces are just in one geographic area, you could take that layer, overlay it with another layer by using a spatial join, and then you very easily have an output that gives you your answer. So this here is an example of a simple polygon overlay. I won't go too far into this because we kind of just went over the idea, but this is something that you can look over, as well as this slide over here, polygon to point. Don't need to worry about this. I want to bring us back over now to talking about our overlays and then our clips, our intersects, our unions. So the output data for an overlay are always going to be the least complex of the inputs. So your order of complexity is going to be a point, a line, or a polygon. Here's an example of your input layer 1 being a point, your input layer 2 being a line. Your output layer is going to be a point because the simplest or the least complex of those 2 data types is the points. If you have a point and a polygon that you're overlaying, your output is still going to be a point. Essentially, the only time that you're going to have a line output layer or a polygon output layer is if both of those layers are lines and polygons. Or if the most complex of the 2 is either a line or a polygon, you'll get the least complex layer as the output of those 2 layers. This here is a very good visual representation of a clip, an intersect, and a union. So we talked about clips earlier. A clip is also a type of overlay in a sense, but what clip will do is it will give you what the underlying data is for one of those layers just within a certain boundary. You see here our bounding layer is this wonky looking polygon, and our data layer is these little bodies of water. The clip is just going to give us the bodies of water that existed between or within that polygon. Now, an intersect is going to maintain the data that is in the bounding layer, as well as the data that it overlays with in the data layer to give you this type of an output. A union will preserve everything. So a union is taking everything in this certain layer, the bounding layer, it's taking everything in your data layer, it's combining the two, and it's giving you everything between the two, but it is showing you where the overlay occurs. So you'll see everything in our data layer that we overlay the bounding layer onto is still preserved there. So now we're looking at a buffer analysis with a spatial join. Here we're interested to see which parcels are going to be impacted by a road improvement project. We're going to use a road layer and a parcel layer in our GIS. We're going to create a buffer around that road feature. We'll use a spatial join to find which parcels intersect with that buffer, and then from there, we can generate the list of impacted parcels, which you see here. So here's an example of a raster overlay instead of the vector overlays that we've been discussing so far. You'll see that in this case, our input layer 1 is a series of A's and B cells. These cells are either labeled as an A or a B, whereas input layer 2 is a series of 1s, 2s, or 3s. The output layer is going to include both the information from layer 1 and the information from layer 2 to have an output layer that has A2, B3, B1, as you see in this figure. If you look at the attribute table, all of the data between input layer 1 and input layer 2 has now been conjoined in that attribute table, as you can see here. A1 now counts for forest, like ID 1 in layer 2 did, and it also accounts for the soil name of Evard Loam, which it did as type A here on input layer 1. Now, raster overlays can become a bit complicated when grid cells are not well aligned. A lot of the times when this happens, we have to resample to convert one grid to conform to another. Or we have to come up with some forms of rules. Rules of hierarchy where either we select the highest value where that overlap occurs, or we try to select a modal value. This is something that you'll get into a little bit more probably throughout this chapter and your next. So now what I'd like to do, I want to just scroll through the rest of these slides and see which ones will be the most beneficial for you to see. Okay, let's start here. We're going to work on the question, or an example here, of which Charlottesville neighborhood contains the highest number of individual real estate parcels. We start with all of our Charlottesville neighborhoods. You can see in our layers we have 10th Page, Barracks Rugby, Belmont, Fifeville, so on and so forth. Each one of these neighborhoods is represented by a different color. We can see that we also have our center lines, our parcel points, and our parcels within these layers here. Looking at our attribute table, you can see your object ID, property ID, parcel spot, address, so on and so forth. We don't have a neighborhood ID in this example, though. In addition, we also don't have a count of our parcels. So what do we want to do? We want to run a spatial join. We're going to run a spatial join. It's going to be an outer join versus an inner join. In this case, we're using an outer join because we've checked keep all targeted fields. We're saying that we want to combine target features, this NHTM93S3 polygon. We want to join it with this other one, our NHTM93S3 polygon, with our output feature being a spatial join. This join is going to be a join one-to-many. Our merge rule is going to be sum, and our match option is going to be intersect. We just want to intersect these two layers. They're essentially the same layer, but each one is missing something. One is missing a neighborhood ID, one is missing a count of parcels. We do this, and now we get this map that has both pieces of information in just one layer. So now we have one row per parcel, including the neighborhood name. You can see that we have Belmont, the count name, Belmont is the name of the neighborhood. Our count is 2107. Fry Spring count 1567, so on and so forth. Other commonly used vector overlay tools are that clip, spatial join, intersection, and union. The clip is that cookie cutter approach that we mentioned. It has the bounding polygon defining the clipped of second layer. So your visual example is right here. What is on the input is defined, or what is put out from the input is defined by what your clip feature size is. That bounding layer is going to be the outline of that cookie cutter for what you select from your data layer. So you see our input here is this square polygon with some water, some land, and some points of interest. Our clip feature is just this circle or this cylinder. Our output is everything in the input that fit within the cookie cutter of that cylinder. In our spatial join, geometry is not altered, and this is something to keep in mind. You don't have any new points, any new lines, or any new polygons. It is just attributes from one table appended to existing attributes in another. And it's all based on spatial coincidence, basically where they overlap. This can get complicated when your polygons or your lines from one layer maybe have too many connections to polygons and lines from another. Essentially, this is the issue of a many-to-one relationship versus a one-to-many relationship or a one-to-one relationship. Either can use duplicate data table lines, or you can statistically summarize data associated with multiple overlaps. I'm going to take that whole last bullet point and I'm going to summarize it to you here. Sometimes polygons or lines are layers that have a lot of data in them where overlap doesn't necessarily overlap perfectly. You may have a line that goes, it forks out like this, and you may have polygons that fork out another way or blob another way. Instead of one line overlapping with a polygon, you may have two lines overlap with a polygon. Essentially, you're going to have an attribute table that has many, many, many connections to it. You need to understand, before you run this process, is a spatial join what you're looking to do? Essentially, do you need all of the information from one layer merged with all the information in another layer in an attribute table? If the answer is yes, spatial join is probably the tool you select. If your answer is no, you may want to use one of these different overlay tools. Maybe you just need to understand where an intersection occurs. Maybe you just need a clip of a certain area where an intersection, a union, or an overlay occurs. So think about these statistical tools or these spatial tools before you run them. They are not one size fits all. There's something that you really do need to think through. Spatial join is one of the most common ones that we use in this course, but it doesn't necessarily mean that it is a solve all. So now talk about intersect. It's going to combine your data from both layers within that bounding area. And this again is your visual representation of what an intersect looks like. It looks like a clip, but it does merge the attributes, whereas clip only keeps the input fields. This here is your intersect tool, and this is another visual representation of what an intersect looks like from your input as well as your intersect feature. So here we have these two rectangles. Our intersect is this cylinder that's placed over top the center of the two of them. Our output is just the area where they all intersect together. Basically, think of like the Venn diagram, wherever everything overlaps, that's the output of an intersect. Then we have union. So this will include all data from both the bounding data layers. So your initial data layer and your bounding data layer, these two, here's a good example that I can give you visually at the moment. These two data layers are going to be completely included in a union, and this is what your output looks like. The final area is always going to be equal to or greater than the largest of the original layers. You will not lose anything in a union. If anything, you will only gain from a union when it comes to your area. Here is your visual example of an area. You have layer 1, which is this set of two purple rectangles. You have layer 2, which is your yellow cylinder. Your output is going to be the union of all of them. You can almost think of it as if like you're hot glue gunning these layers together. Everything stays together. Nothing is lost. Now, we also have some fine points and some identities. This is something I try not to go too into. I just kind of like to go through these slides, but I won't necessarily talk you through them as this is not really something you'll have to use too much. But essentially in fine points, you will use rank if snapping is enabled by providing an XY tolerance. There are ways of using a ratio policy to make it so that when a feature is split, attributes are weighted by the proportion of the area in the split, whether it goes to one side or another. Don't focus on this too hard. We also have a tool called identity. This is a middle ground between a union and an intersect. Using the identity tool, preserve the extent of one of the layers, where that new layer will combine, as in union and intersect, features and attribute tables. This here is an example of an identity. The only thing that's lost in this identity is essentially where nothing merges together. Identity is not quite as often used in my course as the union, the intersect, the spatial join, and the clip, but it is a useful tool just depending again on what it is that you want your output to look like. How much data do you need to be combined and merged? What data are you willing to lose? What data do you have to preserve? So when we overlay vectors, there's one common problem, and this is called a sliver or a sliver polygon. And this is essentially when your polygons from one layer and the next don't fully line up. It can be very difficult to see where these slivers occur, but sometimes when you have a very large display that you project your map upon, you can see those slivers or those misalignments. They can take up very little space, but even though you may not be able to see them super well, they can heavily affect analytical results if there's large slivers. So here's an example. On the left, we have just these two layers that were overlaid with a common boundary. When we zoom in, though, you can see where those slivers occur. One of those boundaries had a more straight edge approach to the boundary, where another one was a much more higher resolution boundary where you see all those wiggles and all those little meanders. The slivers are the misalignments between those two layers. So this here is a common problem. This comes from chapter 4, actually. This is talking about where features occur on several different maps, but don't have the same position relative to each other on maps. What you can do is that you can either redraft the data or you can establish the master boundary. You choose one of the two boundaries and you choose that as the master boundary. So that is the one that you go with and you remove the other one. It's a much simpler solution in my opinion. But again, redrafting is also something that you can do. You can do that from, you can redraft the data from their conflicting sources onto the same base map instead. Or again, choose master boundary if you'd like to do that. This here is a visual example of the state of Virginia, as well as some counties that are on it, detailed versus simple, as you can see in our layers pane here. When you zoom in, you again see this issue. One of these layers has more of these meandering boundaries. The other layer has more straight edge boundaries. We can redefine that common boundary with the highest coordinate accuracy if we want. We can manually identify and remove all those slivers, or we can use snap distance during our overlay. This we'll use low ranks to prioritize data sets, where the value 1 is the most important. So this here is a method of integrating to remove or reduce slivers. In this case, we're going to move vertices in poly 2A to the same location as the vertices in this NHTM 93S3 polygon layer. We're saying that 1, this is the most important layer, this has the highest rank, and we're saying that for our XY tolerance, if they're within 50 meters of one another, we want to snap them. Snap moves to the lowest ranked layer. So we're snapping from here to here. We're going to change this boundary or this layer's boundary from poly 2A to the NHTM layer if that XY tolerance is within 50 meters of one another for these two layers. This is also another option called eliminate. Now we can just essentially say that we want to eliminate one of the boundaries. We are looking at our borders to be eliminated in this red line here. We see our sliver polygons in the yellow, which is essentially saying that between the red and this black line over here, these are misalignments in this yellow color. We can just say eliminate. In this case, we're defining that we want an area of less than 200 to be eliminated in this input layer. We run it and it's gone. Now, if this was a synchronous class, typically something that I would test you guys on, but I would say go ahead on your own time and just look at each of these and try to see if you understand which one of these is, which operation is being described. I'll show you the next slide in a moment where you're going to be able to see what the answer to each of these is. So between these three, and between the tools that you've learned of so far of clip, identity, intersect, and union, can you understand from these visuals which one of those operations is being described? And here you go. So we will finally go through summary statistics. This is a very powerful tool because sometimes you need a statistical summary of your attribute table. To do summary statistics, you need to right-click on any of your fields or columns in an attribute table, right-click on the field that you're interested in, and scroll down to Summarize. From there, you get summary statistics. And from summary statistics, you can select the fields, whether it's, in this case, adults and eggs. You can select what type of statistic you want. In this case, we want to sum them together. And we can also choose how we want to sum them together, whether it's on, in this case, common name or site name. And once we run that, you'll see that the summary statistics from this summarize tool lets you calculate statistical summaries of broken down groups, whether by a 1 or a 2 or a 3 type group. So here again, you saw that we chose common name and site name. You can see them in the case fields here. We chose it for the sum of adults as well as the sum of eggs. Now we have an understanding from our summary statistics of the frequency of where each one of these occurs and the name of what bird it is where each of these occurs. So this brings us all the way back to the very first example that we discussed in this lecture, talking about the 4 or 5 types of birds that we have on the eastern shore, trying to understand their colonies and their colonization habits over the last 20 years. We can now see, based on the adults and based on the eggs, as well as based on the neighborhood and the bird type, what the frequency of their occurrence is. So, all in all, what I'd like for you guys to take away from this lecture 4, spatial data analysis, is selection, both spatial and non-spatial selections, classification, MAUPs, tools like dissolving, proximity and buffering tools, your overlay tools, and your eliminating slivers tools, as well as finally summarize, which you saw in our last example. So with that, that is the end of your lecture 4, and you can go ahead and move on to the rest of your tutorials and your assignments for this section of class, as well as moving on to lecture 5.